This problem says find the Maclaurin series of the given function, f of x equals x e to the x. So now in order to find this function, we're going to have to go way back. So where we're going to go back to is here. So here it is. So do you guys remember this? And this says for the Maclaurin series, f is centered at 0. And that's what we're dealing with here. So anytime we hear that word Maclaurin series, we're dealing with a function centered at 0. So that means our a then is going to be 0. So what we need here now is we need a bunch of derivatives. So that's what we're going to do now. So f of x is e to the x. Now notice this, I didn't take the whole thing. I just want to take this piece right here. And from there, we're going to develop the rest of this. That's what's kind of nice about learning all these other ways to deal with these series. So we don't have to do crazy functions like x e to the x. Because think about it, for each of these, when I do my derivatives, that would be a product rule. That would be horrible. So anyways, so I'm just going to run through my derivatives this way. So f prime of x is going to be e to the x. Isn't this nice? F double prime of x is e to the x. And then all the way down to f nth derivative of x equals e to the x. So now when I go to find all of those f primes of a, f double prime of a, and all that other stuff, for my f of x, when I plug in 0, because remember, it's a Maclaurin series, so that means we're centered at 0, that's going to equal 1. So f prime of 0 is going to equal 1. F double prime of 0 equals 1. And then all the way down to f, the nth derivative of 0 equals 1. So they're all 1. So now think about this. For our Taylor series, that means all these f of a's, f primes of a's, f double primes of a are all going to be 1. So, and also keep in mind here that our a is 0 because we're centered at 0. So these are all just going to be x's, x squareds, x cubes, so on and so forth. So that's what we're going to do now. And keep in mind, we're only doing this for e to the x right now. Okay, so that means our e to the x is going to equal 1 because that's just our f of a plus f prime of a over 1 factorial. So it's going to be 1 over 1 factorial. And I'll just keep this consistency so you guys can see it. X to the first plus 1 over 2 factorial, x squared, plus 1 over 3 factorial, x cubed, and so on and so forth. So I could keep going with this. And then my nth one is going to be plus 1 over n factorial, x to the n, plus dot, dot, dot. And it does keep going. So don't forget, we are just only doing this for e to the x right now. So the series of this thing then is going to be n equals 0 to infinity. And then this is going to be 1 over n factorial times x to the n. So that's what's nice about it. Once I find the nth one, that's really just what I put in front of my sum there, or my sigma, in order to get the series completely. Now we're going to handle the problem that we had. We actually had an x in front of that. So guess what we're going to do? All we're going to do now is take what we've done there and multiply it by x. So then I'm going to move this over a little bit here. Okay, so then I multiply that by x. And that means I multiply this by x. So the cool thing about this now, my series for x e to the x, and all I'm going to do here is times that to the inside here. And this is what we get. Because what do I do when I'm timesing and I have the same base? I just add my exponents. So that's essentially what I do here. So this is the answer for this. So keep in mind, we didn't go through x e to the x, which is cool. because that, like I said, that would have been horrible because we'd have had all these product rules here when we had to do the derivatives and keep doing product rules and product rules. And it gets a lot larger as I continue to do that with derivatives. So it's very nice that we didn't have to do that. But we're able to just use the series of e to the x and just times it by x. It's a beautiful thing. All right, there it is.